if you read all these headlines in the articles, you'll notice that all you say, oh, there's company XYZ or whatever was hacked in a target attack, and be careful, don't open the Word Office documents or attach in suspicious emails. But they never go into details of like how does the attack work, what does it look like, or how do you even detect them. In fact, there's probably no public documentation on this topic. So today, hopefully, we'll try to change that. We'll pretty much tell you everything you ever wanted to know about Office documents and how to all the different techniques you can use to analyze them. And at the end, I'll show you how to write generic antivirus or IDS signatures to detect these vulnerabilities on the wire. All right. So most of these attacks are obviously in the Microsoft Office code, and a lot of it is in the binary file format, which is all the default file format that Office 2003 uses. All versions before 2003 and before. Office 2007 uses the XML file format, so you don't have this problem. All right. So before we go into all the attack details and stuff, we should probably talk about the binary file format first, like how do you parse it and so on. So, all right. So all Office applications like Word, PowerPoint, Excel, Visio, Publisher, they use this file format called the OASS, also known as OLA structured storage file format. And all that is basically, it's literally a file system inside a binary file. So because it represents a file system, it has concepts like directories and files, just like you have in traditional file systems. Except for they don't use the same terminology, right? So instead of calling things a directory, they call it a storage. And instead of calling things a file, they call it a stream. And that's pretty much all there is to it. And parsing it manually can be pretty difficult. So don't try to do it unless you have to. We know because parsing it by hand can be difficult. We have APIs that you can use to parse them. It's not very difficult. You only need to know like 3 or 4 functions to do it. So the first function you need to know is SCG open storage, which you just pass it a file name, and then it will return to you an iStorage object, and then you can use that to enumerate all of the streams or storages inside the file. Sorry if I look like the light's kind of bright. So after you get back an iStorage object, you call enum elements, which enumerates all of the storages and streams in that file. And then once you find the ones that you want, you just call open stream, open storage on that, and then you can call read. It's quite simple. So here it is an example of how to do it using the Win32com API. It's pretty short. It's probably like maybe 20 lines of code. So there you go. And now if you're not familiar with Win32 or C++, and you want to be new school, you can use the Python.com wrapper. You can so all it is just pretty much a wrapper around our com API, and it's much easier to use, and it's very, very simple. Here is an implementation of it in Python. All right, so I've given you pretty much, that's a general description of the OLA structured storage file format. Now we go into the application-specific file format, for example, PowerPoint, Excel, and Word. So I'll go ahead with PowerPoint. So PowerPoint stores all of its data inside the stream called the PowerPoint document stream. So when you call enum elements, you'll see a stream called PowerPoint document. And you can open up that stream as a buffer. You do whatever you want with it. There are 2 data structures in PowerPoint that you need to be aware of. One is called a container, which is the same as a directory. And the other one is an atom, which is just a file. So a container can contain 1 or more atoms or other containers. An atom, just by itself can't contain anything. And all the records they follow TOV style, so that's type length value. Each of the records have a header. It'll tell you what it's a 8-byte header. It'll tell you what type it is, if it's a container or an atom, and so on. So this is the structure. It's pretty simple. And so the thing to notice here is, in order to distinguish a record from, to identify if a record is a container or an atom, you just look at the record version. If it's equal to XF, then it's a container. If you have anything else, it's an atom. And the record type is refers to the PowerPoint record type. And these are the record types that we documented in the PowerPoint file format that we released to the public earlier in February this year. So there are about 100 of them. All you do is you just figure out what the number is, and you go open this file spec, look at the table content, click on it, and it'll tell you exactly what the structure is, what each of the members is, and all the definitions, and so on. This is another picture that I drew. Might be a little bit easier to see. All right. So how do you parse this? This is, I guess, a diagram to show how you would parse it. So basically what you do for PowerPoint is you open up the file, you open up the PowerPoint document stream, you figure out how large that stream is, you read all of it into a buffer, and then you check the first 8 bytes. You check, okay, well, to see if it starts with a container or an atom. If it's a container, then it'll tell you how big it is, and then you read the next data block. You do this recursively until you've exhausted all the data. And that's pretty much all there is to it. I mean, it's pretty simple. How many of you ever actually wrote PowerPoint parsers before? One person in the back. Was it difficult? Yes, he said. So just in case you decide to implement your own PowerPoint parser, this is, you want to check your work. So this is a picture of what it would look, a normal document would look like. So this is actually a diagram of a real PowerPoint document that I made. If you notice, the first record is a document container, type OX3EA. And then you notice inside that container there's a document atom, and then there's an environment container, and there's like header, footers, and so on. And if you notice towards the end, in the middle, there's a slide, 2 slide containers. So pretty much, the concept behind PowerPoint is that things are represented as the unit of representation is a slide, right? So for each slide you have, there's a slide container that describes the characteristics of each of the slides, so like slide ID and so on. Cool. All right, so if you want, this is actually an excerpt from the PowerPoint file spec. So you ever want to know, okay, well, I found a record type 1001. And so you look it up and you say, oh, that's a document atom, and then it'll tell you pretty much the structure describing that atom and what each of it means. Here's another one. Here's a slide atom. Let's see if you notice, show you a slide layout descriptor and the slide ID, so on. So it's pretty simple. All right, so I pretty much told you how to parse Office, how to write a PowerPoint parser within, I don't know, 15 minutes, 10 minutes. So it's pretty easy to do. You can do the same thing with Excel and Word. All you have to do is just read the file format specification, and then you can figure it out from there. It's not that hard. So now I will show you an actual exploit of what this would look like. The way these exploits work is that the attacker will determine, he'll say, okay, well, I need to attack company XYZ, so they perform reconnaissance on the person that they need to attack. For example, like say it's a CEO of a company or something like that, or a researcher. And then they'll figure out, what this person does, who he reports to, who are some of his peers, what kind of conference or professional conference he goes to. Example, in my case, it'd be like Black Hat. So based on all this reconnaissance information, they can craft a fairly persuasive email message to send to the person, and then along with it, there'll be an Office attachment. It'll say, please open it. This is a call for paper. Please open it up, or something like that. And the person, if he's not trained in these email security policies, he'll like, oh, cool, and then he'll just double click on it, and bam, that's it. You double click on it, you'll see a normal document open, but just like you would normally expect. But in the back end, we're already dropping like a Trojan already, and by now they already have access to all the information on your computer. And if you're on CorpNet, they now have access to all the information on your CorpNet. So here's a demo. Give me a second. So this one, the attack. So this one, I assume I'll be attacking somebody that's going to Black Hat, some security researcher. So I'll send an email to him. It's like, hey, dude, this is the Black Hat Japan 2008 call for paper. Please open it up or something like that. Here, you open it up. And there you go. Stuff like that, right? So in this case, I made it launch calc.exe. In most cases, obviously it won't launch calc.exe, but they'll launch, a rootkit or something like that. So, yay, the demo worked. Okay. All right, so Shift F5. All right, so I show you what an actual exploit looks like. Let me go ahead and tell you how to defend yourself first. So the first obvious option is to have the latest security updates. I know this sounds obvious, but the thing is, most of these target attacks, they exploit Office vulnerabilities that's like 2 years old. Sometimes, most of the time it's already patched. So if you have the latest Office security updates, then you wouldn't be affected by these. So always make sure that you have the latest security updates. It helps to patch. The second option you can use is MARS. So in the previous one, it's already patched, but what if it's a 0-day? How are you going to deal with it? So we came with MARS. So basically what MARS does is it converts the binary file format into XML file format and then reopens it up. So this is the main reason why you see one of the prerequisites is the Office 2007 compatibility pack. It just requires Office 2003. So and most time by the time they convert the binary file format into the new XML file format, the exploit won't work anymore. So you'll be protected. This works on, even if it's a 0-day. The other one is if you have Office 2003 SP3. So Office 2003 SP3 is actually the result of major security pushes and an application BSDL. So we fixed a lot of bugs there. So an interesting fact is that if you had Office 2003 SP3, then you will not be affected by any of the Office attacks that we've acknowledged in the public. So if you don't get anything out of this talk, go home and install Office 2003 SP3, and you'll be safe. So if you combine Office 2003 SP3 and MOIS, you get double the protection. So they actually having both of them actually mitigates or eliminates a lot of the Office vulnerabilities. Obviously the last one is you can use Office 2007, which doesn't use the binary file format. So you can buy the home edition for like $60. So I'm not lying. It's true. It's true. All right. So I talked about the defensive mechanism. So now let's go into the meat of the talk. So you have a malicious or a file that you suspect to be malicious. How do you go about analyzing these things? So the first thing to know it's really nothing out of the ordinary. It's just like any other Office bugs are just like any other application bugs. We still have stack overflows, heap overflows. It's all over the integer overflows. It's all over the place. It's nothing like completely new. None of these bugs are new, or like at least the class of vulnerabilities. And the basic structure of the exploit is you'll always have shellcode, and then you have a malware component, and then you have a clean document. The clean document is the document that you actually see when the exploit runs. So in my case, that was the Black Hat Japan 2008 call for paper that I made up. And then some of the techniques that they use, the majority of them are fairly well known. I mean, we've seen these in the last maybe 7 or 8 years. Some of them are particularly unique, so we'll go into that later. All right, so this is actually a picture, a diagram of an example, a typical Office exploit. You have an OASS header, which is all OASS file has this, and then you have some legitimate Office records. And then you have some shellcode, and then maybe it might be followed by some other legitimate Office records. And then you have the Trojan or malware, and then it'll have the clean document. If you notice, everything is self-contained. They don't need to phone home to download a Trojan at all. So it's not a Trojan downloader. And then again, this is a typical layout of an exploit. There could be variations to them, but most of the time it follows this convention. All right, the techniques they use, standard GetEIP to do position independent. So that's jump call pop. And about 99% of the time, the shellcode would be encrypted. So they'll have custom decoders, be like, XOR against 1 byte key, 2 byte, 3 bytes, 4 bytes, sliding window, the whole shebang. So most of the time it's not very obvious what, the entire shellcode is not going to be so obvious to you. Maybe the decoder step will be the only one that you'll see. And then you have PEP retrieval, this is fairly standard in Win32 Win32 shellcode. And then the last two is somewhat unique. So this is file handle brute force. So what they'll do is they'll try to brute force each of the file handle. I'll go into that a little bit and I'll explain why they need to do that. And then they'll quit application relaunch. This is, if you notice in the demo, when you launch this, Office actually launch and then it goes to one screen and it quits and then it relaunches again. That's actually because they exit the process and then relaunch it again to open a new document. That's why you see no crashes. All right, so why do they use file handle brute force? So when Office opens a file document, most of it will be mapped in memory. So in the case of the last example, I opened up a Word document. So this entire Word document will be mapped in memory, and the exploit needs to find where the document is mapped in memory, right? So in order to do that, it can either scan the entire process space, which probably not very wise. So what they do is they brute force a file handle. What they'll do is for each file handle, they'll open it up. They'll call get file size on it, and then Windows will return the file size. And then they'll compare the file size against a known file size, like the real file size that they have. And then obviously because Office has this file open, you have a file handle, right? So if it's successful, they will find a file handle that corresponds to this Office documents. And then if they find it, then they'll have the handle, and that's it. And the reason why they need to find this is because the exploit and the Trojan and rootkit and the clean document are stored at specific offsets inside the physical document. So one could be like stored at offset OX 2000 or something like that. So once they find themselves, they'll seek to that position, to that offset, then extract however long the Trojan is, and they'll write that file to disk. Most of the time they'll be in the temp folder, and then they'll call WinExec on it. Same thing with the clean document. It will be stored at some offset inside the file that they'll know ahead of time. So, once they find the file handle, that's it's pretty much game over then. So, if I went too fast, this is a summary of it. So in the beginning, you have the shellcode decoders. It'll decrypt itself. Then it'll run. Then it'll build up a list of function pointers. So for set file pointer, read file, write file, close file, WinExec, exit process. These are fairly standard, create file as well. I didn't put it in there, but these are fairly standard Win32 API calls that you would need to use to achieve some of the functionalities I just talked about. And then once it, then it tries to find itself in memory using the file handle brute force method. And then it'll extract the file using literally set file pointer and then read file, write file. And then once it extracts the Trojan, then it'll run it, and then they do the same thing for the clean document, and then it exits the current process. So you'll never see a crash. Nowadays, even you have a really slow computer, you might be able to see the application running and then quitting and then relaunching. But if it's a fast computer, you might not be able to see it. It's very quick. It looks like it's the real deal. Like sometimes I get tricked by it. So, all right. So for analysis, what kind of tools do you need to analyze these things? Obviously, this is not an exe file, so you can't use a debugger to open it up. So the tools you need it's very simple. You need a hex editor, disassembler, and optionally a debugger. You can use WinDBG or OllyDBG. It doesn't matter which one. I prefer WinDBG because it has some pretty convenient commands that you'll need to use later. And so the objective when you analyze these documents is 1, to identify the shellcode. That's the most important thing. 2, understand what it does. And 3, extract the malicious Trojan or /clean documents. And then, if you have time or if you need to, identify the exact vulnerability that it was exploiting. All right, so debugging Word document. How do you do this? There are 2 ways you can do applying static technique. So all you do is you literally open this file up in a hex editor, and then use your opcode reading ninja skills and figure out where it is, where the beginning part of it is, and then you read it and make sure that you have a correct understanding of it. And then the dynamic method is a little bit easier, and it's actually more interesting, which I'll go into. All right, so this is some opcodes. I know there are a whole bunch of AV people here. I probably recognize most of these opcodes, if not all of them. The most crucial part when analyzing this was you have to be able to identify the shellcode. And because when you open this up in a hex editor, it's just a whole bunch of bytes, right? So you have to be able to recognize sequence of bytes that may look like legitimate code. So you need to be able to do that. So anybody here recognizing these opcodes besides the obvious ones? I will give you a free Office T-shirt if you find some. All right. So an EB is just a jump, and then you'll see, and towards the end you'll see an EA, EB, FF. That's a backwards call, and then this is pretty standard jump call pop. And then the second bullet, the 63A1300. I think most people should know this one. Anybody know this one? This is move EAX FS30. So the 64 is a prefix. So any instruction that uses the FS segment will have 64 in front of it. And if you move to EAX, it'll be an A1. The next one is 648B1D30. This one is if you move to EBX. It's the same thing. This is literally move EBX FS30. And the last one is D9724F4. This is the FNSCNV. Pretty much is another way of getting EIP. This is actually the one that lots of the Metasploit encoders use. All right, so method one. So assuming by this point you are identified where the shellcode is, so you make sure you patch in the beginning of it or whatever with OXCC, which all of you probably know what this is. It's a software breakpoint. And then you patch a few bytes with OXCC, and then you start up Office. And then you attach the debugger to it, and you let it go. And then you open up the document, and if you did it right, the software breakpoint should hit, and the debugger should jump in, and then you can single step through it, do whatever you want. If nothing happens, then you're probably screwed. You have misidentified the shellcode, and by now you are probably owned. But again, of course, most of the time people recognize it correctly, so. This is no problem. All right, so method two. This is a pretty common one that AV people use. You just pick up any executable you want, copy the shellcode to the entry point, and just open up a debugger and just set a breakpoint there and single step, just like you would do with while debugging any other exe file. Pretty simple. But this one requires you actually have to manually. All the previous two methods, there are some disadvantages. One, you actually need to have a hex editor to edit these files, the bytes, right? So. Say sometimes you're in an environment you don't have a hex editor. That could happen. So you can use these methods. This one just requires WinDBG. This is actually quite interesting. Anyone here use WinDBG? Yay, lots of people. Anyone know what dvlock and remem do? Jonathan, you don't count, man. Jonathan's my boss. So basically, dvlock just allocates a block of memory and with read, write, and execute in the current process. And then remem reads the content of a file on disk to whatever you want in memory. So some of you can probably already figure out why we want to use these two functions. So basically, what you do is just once you get the sample, rename it to blah whatever .bin, and then you open up any process you want, and then attach a debugger to that process, and then you run dvlock. And allocate a block of memory that's either the same or greater than the size of the physical file on disk. And then you read that entire content, the file content into the block of memory you just allocated. And then, because you already know where the shellcode is, so now you can go down and figure out it's where it is in memory, right? So then you set, you do just REIP equal to wherever that memory address is, and then you single step. And then now you'll be single stepping the shellcode just as you would in the exe file. So it's pretty easy. All right, but this method also has a disadvantages. If you remember earlier, I talked about the file handle brute force. So this one, we don't even open the file at all, right? So when the shellcode runs and it tries to find itself, it's going to go into a loop that's going to go on for a very long time, right? So you'll never get there. So that's why we use the next method. Ignore this. The next method, this is the best one, and this one I use, is that you do the same thing as the last one, but instead of opening any process, you open up like, hex editor, notepad, vim, whatever, or even just write a simple C program, like fopen, blah, RB in binary mode. And attach the process, attach a debugger to that. And the reason why you want to do this is because now you're inside that process, and that you know that process has a file handle that has the exact same file size because you opened it. And then you do the same thing. You set EIP to the beginning of the shellcode, and now you will actually the file handle brute forcing will actually be successful, and you'll just be analyzing just like the shellcode will now execute just like it would in a normal in a normal successful exploit. So it's pretty easy. But this requires WinDBG, so you should all use WinDBG anyways. Alright, so now you know how to analyze. I just showed you how to analyze it. I mean, that's all there is to it. It's not. The only hard part is that you actually have to remember a lot of opcodes. But I think after you do this for a while, you can remember most of them. Alright, so now that you've analyzed these things and you know that's bad, you need to be able to detect it on a wire or, whatever. So the things that you need to do is, one, you need to identify the fingerprint, the OLA file. So it has to be a legitimate OLA file. So an all OASS file have, the first 8 bytes is always the same. DLCF11, E0, A1, B1, 1A, E1. You want to make sure that, it's a legitimate OLA file. And then once you, are certain that it's an OASS file, you've got to fingerprint the application. You need to figure out, okay, well, is this a Microsoft Word document? Is this a PowerPoint document? Or is it an Excel spreadsheet? And the way you do that is, you either use the COM API that I talked about earlier, you enumerate all the storage in streams, and you look at the stream name. So in PowerPoint, it will be PowerPoint document stream. In Excel, it could be workbook. In Word, it will be like Word. So that's how you would be able to figure it out. And then you parse the stream content. You just read you just call read on it, and then read the entire content into a buffer. And then you can parse all the records accordingly, just like I showed earlier. And then that's pretty much all there is to it. All right, so with all the information I've provided here, accompanied by the Office file format specification that we released to the public, you should be able to write, you should have more than enough information to write your own Office record parser. And maybe even check the validity of each of these of the records. All right. However, to write good IDS AV signatures, you usually need to understand the exact vulnerability, right? You don't want to write something that just catch all, because you have a massive amount of false positive, and your customers won't be very happy. So usually the way you do that is you either reverse engineer the patch and then try to make the best judgment about what the vulnerability is. For Office, it's just a little bit different. For Office, you can actually bin diff the patch, obviously just like any other patch, and you can actually say, okay, what is the Stack Overflow here? But then you won't be able to. It's very difficult to figure out, okay, well, what records cause, what record values can cause this vulnerability? What triggers this vulnerability? How do I get here? It's a little bit more difficult, and it's not as obvious. Or the other option you can do is we'll just give you the vulnerability details. And so this is what the MAPP program is. So I work on a team that produces the data for the MAPP program. So pretty much, if you went to Steve's talk, I think he probably told you guys about MAPP. And pretty much what it is you'll get the information, if you're eligible for it, you get the information before Patch Tuesday. And what do you get? You get a technical description of vulnerability, literally exactly what the problem is, and then a repro file that you can go use in your lab. Or if it's a network vulnerability, you'll get a packet trace or a PCAP file, and then you'll get a crash dump. And then you can get obviously with stack trace and it's annotated disassembly. And then you also have detection logic. So this is for Office, for network vulnerabilities, it's a little bit easier. But for Office vulnerabilities, we will tell you exactly what records are affected, what value inside those records are affected. So you can actually write signatures to pinpoint the exact vulnerability. So minimal false positive. So I thought this is an example of what you'll get. This is MS-08-014. This is an Excel vulnerability that we patched a few months ago. If you see, you'll get, this is the description you'll get. This was done by a colleague of mine, Rob. So you say, oh, this is an uninitialized stack variable, pre-populated with the attacker controlled value. And then for the detection guidance, I'm not going to read out the entire thing because that will bore you. But if you look at the stuff in bold, for detection guidance, we tell you, okay, well, if you find an OX record type OXDF with no preceding bound sheet records, these are Excel-specific terminology. If you read, they're all documented inside the Excel file spec. So if you don't know what I'm talking about here, I mean, it's all inside the Excel file spec. So, I mean, given this level of detail, you should be able to translate the technical description into whatever antivirus engine that you use or IDS IDS product that you use. So it's pretty easy. All right, the next one is this is a network case. So this is a PGM that we released a few months ago as well. This is a DLS, and I'll tell you, I handle this case, so I pretty much told you, okay, well, this is involving PGM where it doesn't parse the option length field. And here is I'll give you a packet dump of some network capture that actually triggered this vulnerability. And then under the guidance, you say, oh, it's just check what PGM packets with invalid option values and option length equal to 0. So it's pretty. Given all this guidance, you can write very accurate IDS AV signatures. All right. So some acknowledgement. There are a lot of people, who helped me on this the presentation. So Rob, my colleague, Jonathan, my boss, Damien, who's not here, Furman, my office mate, Brian, Dave, Dustin, Terry, and a lot of people from MSRC and SWI. I love you guys. And of course, the office team. They are great people. Office team? Yeah! They're very good people. And then that's it. So my team, we have a blog where we talk about vulnerabilities. We'll give details where details that could not be put in the official bulletin that you see every Tuesday. And it's actually written by the people who triage these vulnerabilities. And if you have bugs to report, send them to securemarkshop.com. Or if you have malicious Office documents that you don't want to analyze or you don't know how, send them to me. And send them to us, and we'll help you analyze them. And that's my email address, bd@markshop.com. And I will now open this up for questions.
Hi there. One question for you.
Yeah.
You mentioned that Office 2007 was a good mitigation against these binary file format attacks. Are you aware of any vulnerabilities that have been identified? Obviously, Microsoft 07 or Office 07 still parses these file formats.
That's correct.
Supports them. Is there any code shared between 03 and 07? Also, have been any identified vulnerabilities shared between the two code bases when it comes to parsing these binary OLE streams?
Interesting. So basically, what his question is. Are there code in Office 2007 that parses binary file format and hence may be vulnerable to these bugs or whatever, right? Am I understanding that correctly?
Yeah.
Okay. So basically, if you look at all the bulletins that we release every month, we'll tell you list the affected products, and you can see if Office 2007 is affected or not. Well, clearly, obviously, there are code inside Office 2007 that parses binary file format because we need it for backward. Because Office 2007 needs to be able to parse the old file format as well, right? So yes, there are some code that's shared.
Thanks.
Yeah. Anybody else? There's another person. Okay.
So you talked about the CDF format, compound document object. Are you aware of any cases where reordering of elements inside CDF could cause vulnerability signatures to be bypassed or evaded?
No, right? Because his question is, well, if I reorder these records, would that bypass the parsing code? Is that what you're asking?
Yeah. For example, if you have to give an example, let's say a doc file is being sent over the network. Mm-hmm. And a device is trying to parse a doc file.
Right.
And it's a sizable file, it's a big file. So if records are reordered, I mean,
Okay, yeah, I understand your question. Okay, so basically, if you reorder the records, then that would depend on the Office application, right? The parser will say, well, this is part invalid, and the Office won't even open it. It will be a corrupted file, right? I don't know if that answers your question. So if you reorder correctly, Office may open it. But if you don't reorder it correctly, then Office will say, well, the Office parser has sanity checking, and it'll say, oh, okay, well, these records don't make any sense, and so it's a corrupted Office file, and I'll tell you.
So you're saying that? Well, the question was if you've seen any real-world attacks using that technique.
I've seen vulnerabilities that do that. Where the record orders actually matter, yes, we've seen that.
But not real attacks.
I'm not understanding. So you're saying, have I seen real live samples? That
you gave an example of an attack. Well, in this case, there was just a calc being executed. But have you seen any malware or any attacks using that reordering approach?
Probably. I'm not sure, to be honest with you, because you usually don't look at the order, because the Office parser will take care of that part for me. And it doesn't even matter if it's reordered, because if I use a COM API and I read it, it doesn't matter if it's reordered in what way. I'll still be with the parser, all right? So, yeah. Sorry, I hope that answers your question, yeah.
I have a question.
Yeah.
Do you know if they are going to or have updated the binary file format specifications that were released? In the past, I've looked at some of the ones that we got through some licensing program, and there were some inconsistencies and some things that didn't make sense, like where some field, turned out in a real document to be, 6 billion or something, which would cause a memory overflow in a parser. But somehow Microsoft Word knows how to read this, but I don't.
I think we released an update. We recently. Is anybody from the Office team, or you can talk to the Office team, and they can tell you more. I think there are some updates to it.
It's more up to date to any bugs or anything that used to be in the old one. Thanks.
Do you have any recommendations for an OA object browser that's publicly available to make just looking through all the objects any easier?
You can actually write your own. It's pretty easy. It's like 20 lines of code. But yeah, there are some freely available ones. I think OA Viewer or something like that.
Yeah. Do you have any personal favorites or recommendations for?
No, not really. We have our own tools that do this. So, yeah. I mean, I just showed you the Python example. You can do this in like 10 lines. So, yeah. I mean, there's some that you can use. The one I can name is like OA View or something like that. You just go to live.com and search for that. It'll tell you.
All right. Thanks.
Yeah. Yep.
Are you saying that if I switch to Office 2007, Office 2007 is not vulnerable for any other attacks?
I would be lying to you if I were to tell you that. It's like saying like there's no bugs in any software, right? No. Yeah, sure. I mean, there could still be bugs in Office 2007. I mean, we try our best. I mean, that's what we have the SDL there for, right? We try our best to write solid code and make sure the code doesn't have minimal amount of vulnerability, but we'll never get to 0 bugs. But I mean, Office 2007 is quite solid. I have great confidence in the Office team. Yeah. So yeah, is that it? Yeah. Yeah. So that's pretty much it. You now know everything you need to know to analyze target attacks with Office documents. Pretty simple. All right. Thanks.